I'm very happy to be able to introduce our next keynote speaker, Luke Zettlemoyer. So I have to start this introduction with Luke's undergraduate education at NC State, where he actually got into AI working with one of our farmer AI lab PhDs, James Lester. And he happened to read some of my papers on semantic parsing at that time, thanks to James' recommendation. He then went off to do his PhD at MIT with Mike Collins and became the leader in semantic parsing, a topic that him and I both know is very dear to my heart. But then since then, he's gone on to do an amazing lot of things within NLP. If people don't know, Elmo was really the thing that started the current, large language model world that we're on. It was just one of the many things past his semantic parsing era that Luke has done. He's become a leader in the NLP community, generated amazing students that have now gone on to faculty positions all around the country and the world. I was talking to Antoine actually at EPFL, and our own Ansel Choi, who's over here. So he's a real leader in the field, and I'm very happy to be able to introduce him today to talk about this brain transmerge. I was just making a joke to him. I can't compositionally compose the meaning of that phrase from its individual words, which is an inside joke between Luke and me. So I'm interested in seeing what it's about.
Yeah, I'm super into compositional semantics over the years, so I sometimes a little bit over-index on having some hard to understand phrases. I find it fun. Yeah, I keep promising Ray and also I'll come back and give a talk at some point. So I really appreciate the invitation, and it's really fun for me to be here. I have a fair number of connections over the years to UT. This is joint work between the University of Washington and Meta, and Sachin and Margaret, who are credited here, were the leads on some of these projects, so they really, really deserve all the credit. But of course, anything I mess up is my fault and not theirs. So what does this branch chain merge really mean? The goal for the talk today, this is a pretty technical talk about language models, but also pretty accessible, I hope. You can give me feedback. Actually, like questions along the way, although that's not the format here. So if you have something pressing, just yell it out and I'll adjust, but we'll mostly do questions at the end. My goal here is to think about how to reinvent the training of large language models. We have a recipe that OpenAI invented. It works. We've been talking about it all of these 2 days. We've been talking about it for years, but it's not the end. There are problems. We need new ways of thinking about how to train these models. And when I think about doing that, you need something to anchor on. And for me, in this space, data is everything. The data is what makes the models work, and then sort of getting sufficient compute to actually train on it and getting on the right scaling laws. So you need to really focus on data, but you also need to think about the compute environment. And although you are going to have an amazing new compute environment coming soon with hundreds of GPUs, you'll be able to do some of this training. The biggest models in the world are going to be training on hundreds of thousands of GPUs and gigantic supercomputers that are just completely inaccessible. So how do we focus on data, and how do we invent new training regimes that don't require that much supercomputers? That's really the focus of the talk today. Okay. And of course, I don't really have to provide data to convince you that data is everything, but you've seen many, many curves like this. I think this is even Llama 1 on the right, not Llama 3, which came out yesterday. But to a first approximation, we can argue about chinchilla, we can argue about scaling laws, but you keep training these models and they just keep getting better. And part of that is just giving them more and more data, because every time you scale up, you don't just grow the number of parameters, you also grow the amount of data. A lot of people don't think about that, but it's absolutely crucial for the progress that you make. But current models use the data homogeneously. What does that mean? It means you have this gigantic language model, hundreds of billions of parameters and trillions of data points, and every single parameter is updated on every single data point. And it's a super hard systems problem, super hard supercomputing problem, but it's super fascinating that it works. It's the trend of the day, but it does actually limit scaling, and it has other limitations for how we do things. Just a few random issues that we've worked on over the recent years. I won't solve them all today, but just to kind of get us all in the right mindset that we need new algorithms. It can hurt generalization by emphasizing domains based on their prevalence. So data balancing, like exactly which subsets of the data you train in which proportions, is absolutely crucial for getting these models to work, and it's almost entirely hidden in the last round of models. It's now a trade secret that the companies don't share. And it actually has strong implications for science. Efficiency with all that synchronization, I think that's pretty clear. But even in the biggest models, even just doing inference, doing forward passes is out of reach for most people. It's fascinating. There's issues of flexibility and forgetting. So even the biggest models in the world don't memorize everything in their data. And if you further train them, they will forget things they've learned before, which is less than ideal. And there's a lot of risk. And so this panel that we just came from did a much better job of this than I did, but there's a lot of risk in thinking about how you use your data, unintended consequences. And because it's so expensive and it's so monolithic, you're sort of baked in. It's hard to adjust after you've trained the model. But again, being very data focused, and again, the numbers have gotten bigger since I made this talk. First draft, or Sachin and Margaret made this talk, I don't know, 6 months ago or something. But you have all this gigantic web crawl data. And the insight that we're going to use for the talk today is that not all data is the same. So in the web crawl, there are many different types of data. There's tech data, there's news data, there's data about sports, there's data about health, data about science. And we need to have some way of getting some sort of structure into our models, some different way of training them. This is not the only way to do it, but it's a great example and it works really well. And you could do it based on language, you could do it based on other things, but this is where we'll talk today. Where we're going towards is, instead of this monolithic training all the parameters on all the data, we want to invent new algorithms that are modular. So we would like different parts of the model to specialize in different ways. And for today, the purpose will be specialized to different parts of the data. But again, other ways of specializing are absolutely possible. But what we really want is not just modularity, but flexibility. So these different modules, we should be able to add, mix, and remove them as necessary, even after training the model. So we can fundamentally change what's being used within the model very efficiently and flexibly at every stage of the process. And this is going to allow an amount of customization and flexibility, which I hope will become clear as we go through the talk, which is very, very different from how the big dense models work today. And where we would like to get to with this research agenda, again, not today, but longer term, is a decentralized language modeling future. So the idea is that a single language model will have lots of different pieces. This is what these little boxes represent, different parts of the model, that can actually be asynchronously developed. So maybe UT owns some of them, maybe UW owns some of them, maybe other open consortiums own some pieces. They can sort of divide by data, they can divide by other things. There's many different sort of research questions about how to do this. But you can, for example, then share computation. So maybe you guys have a bunch of GPUs here. You can take a big chunk. Some researchers in a lower resourced environment, they may have to take a smaller chunk, but they can still contribute. And somehow all the chunks can be put together to make a model that's much, much better than the sum of the parts. Okay, that's the dream. That's the longer term vision here. What we're going to do today is take some steps towards that goal. So I'm going to tell you about how to do modular training. I'm going to tell you how to do asynchronous or embarrassingly parallel training of the different parts. And I'll talk to you about how you get an overall model that has sparsity properties. So when you combine that model together, for different inputs, you may use different parts of the model. It's going to have some sort of, if you know mixture of experts or conditional compute, it will have sort of that flavor in the end. I'll spend the majority of the talk on part 1, and I'll adjust part 2 based on timing and how things are going. In part 1, we'll do a basic version of the algorithm that works really well, but makes certain unrealistic assumptions about how you know what types of data you have. And in part 2, we'll do some clustering and relax those assumptions. So how is this going to work? Just to review how expensive things are, and this is the one slide I managed to update this morning. Even the announcement yesterday for Llama 3 shows, you're training on 16,000 H100s now for months for these models, right? So we really, really need to think about how can we do other approaches. This is, I don't know the exact numbers, but this is well beyond the reach of academia or most of the world. Okay, so what's the alternative? That's conditional compute. And in conditional compute, in a dense training, every parameter on every update. In conditional compute, only a subset of the parameters are updated on each example. So either during training or during inference, you activate only parts of the model as necessary. And this has been going on for a while. Actually, and this graph is does not important, but it's just showing that you can get much better performance by doing this at reasonable costs. The idea is pretty old. I think Hinton, like all great ideas, they all come from the older neural net literature. Hinton had this idea in the 90s. It's been around for a while. More recently, even in the last 5 years, there's been a lot of work. I don't have the more recent citations, but Mixtral and these other models, of course, have become famous over the last few months even for adopting these types of approaches. But they can be a little bit fickle, and they have these kind of load balancing components. It can be quite tricky to get it to train right. And one thing, the way to think about what I'm telling you today is that it's a mixture of experts or a conditional compute approach that's in some ways designed to be as simple as possible and as easy to train as possible. That gets rid of all these load balancing issues that previous models had. And the way we do that is by leveraging the structure in our data, knowing about different subparts of the data and using that for different parts of the model. We're going to do this in the setting of a transformer. If you don't know transformers, it's fine. This isn't an important detail. But fun fact, if you haven't spent a lot of time scaling transformers, every layer has a self-attention layer and a feed-forward layer, sub-layer. We're all really obsessed with the n-squared cost of self-attention. With respect to scaling, this actually just really doesn't matter at all, okay? When you scale up to really big models, like hundreds of billions of parameters, you're almost exclusively, of course, you could get more layers, but you're almost exclusively scaling the size of the feed-forward network. That's what you can see in the graph here. And for the very biggest models, 95% of the compute is spent in the feed-forward. That's where it memorizes all the facts about the world. That's where all the sort of hard work is going on, okay? And so the real sort of juice or the real sort of advantage you can get for efficiency is going after that feed-forward. That's where you're going to get the big gains. And that's what mixture of experts does, right? That's the part that you mixture over. About a few years ago now, we did a first version of this where it was more sort of G-shard or mixtural style. What we did is we just focused on that feed forward, and we did deterministic routing. So for that part of the network, you just had a deterministic bit of knowing what domain of your data are you in. Are you in science? Are you in news? Are you in something else? And then we just separate those parameters by domain and train those parameters separately per domain. And let everything else mix and train overall. This works, actually really well. You get better training than dense training when you do this, and it'll be a baseline that we'll compare to later when we do even more simplification, even less synchronization of the different parts of the model. Okay, so for the folks that know a little bit more about how training works, I'll give you a little bit deeper dive on that concept I just said. When you think about training these models, the real challenge is that you're going to have multiple GPUs across multiple nodes. And communication within a node is cheap and easy, but communication across nodes is hard and expensive, even if you have InfiniBand, right? So there's some cost associated with this. In typical dense training, the way it's set up is, and here I'm just kind of abstracting the transformer to just separate feed forward versus self-attention, even though, of course, it's a full transformer. In dense training, you need to synchronize everything, and you randomize your data. And that's why it's so hard to train, because all this information is constantly being synchronized across all the different layers, all the different data. And the sort of prior work that we did, this demix training, what we did is we said, okay, the feed forward will be separated by domain. So that part of the network, and this is what I was just saying 2 slides ago, that we can just have different data on different GPUs, and it saves us a lot of communication cost. We don't need to synchronize that. We can train that completely independently, but there's still a fair bit of other synchronization going on. So you can, in practice, you get more parameters, but you get faster training, and you get the same inference cost. But big parts of the model are still synchronized. And then the goal for the talk today is, let's just keep on this trend. Let's basically say, how close can we get to synchronizing absolutely nothing? Okay. So the embarrassingly parallel training or the branch train merge I'll talk to you about today is literally that. Again, these don't have to be a single GPU. You can train different model sizes, but conceptually, you have a different model on every single GPU. You're training them completely independently, but somehow you design an algorithm, even though there was no communication during training, they fit together in a beautiful way after training. That's much more than just training n independent models and ensembling them. Okay, and that's what I need to get you through with the algorithm. Mm-hmm. That's right. So if you knew the domain at test time, things are simple. And I'll teach you what you do when you don't in about 6 slides or so. Yep. That's correct. No gradients being passed back and forth. Completely independent data, completely independent training. Correct. The previous slides, the self-attention were synchronized, and there was more, but the data was not. Okay, so where we're going to end up is with a model that's a new way of thinking about a model. So the final model, we're going to call this Elm Forest, and it's just a big bag of models. It's a set of elementary language models, ELMs. Each one of those is actually an independent model. And so conceptually, it's a very, very simple data structure. But over the next kind of 8 slides or so, I've got to teach you how it's trained, because just looking at this data structure, it just looks like n models. But it's been very carefully trained, and we set up the inference very carefully, so they actually collectively work together a whole lot better than they were just independent models that you downloaded from some repository or something. Does that make sense? And so I'm going to do this in 2 stages. I'm actually first going to teach you how we do inference, because that'll be a sub piece we're going to need during training. So if I had trained a bunch of models that like play nicely with each other, how would I combine them to actually assign probabilities or generate text? We'll do that first for a few slides, and then I'll come back and show you the full branch train merge algorithm, how we actually do the training. And then we'll do a whole bunch of experimental results, and then we'll get rid of some simplifying assumptions and do it all again. Okay? So how would we do inference? And this is already a great question. So if you knew the domain at test time, very easy, you just pick out that expert, you use it. That works, but it's naive, it's too rigid, it's not realistic in practice. Instead, we're going to actually have 2 different alternatives. So you can ensemble the set of models, weighted according to the kinds of text you're doing inference for, or you can actually average models. So think of, if you know literature on model soups, you can literally take some subset of the models and average their parameters in parameter space, create a new model that's the size of any of the original models, and do inference with that. Okay, so I'm going to first tell you how we do the ensembling and how we get the weights. And then we use those same weights to do a weighted average for the averaging. So for ensembling, what you need really is, as the text is coming in, either token by token or in chunks, you need to estimate some distribution over kind of which domains that you previously saw that are most like the new test domain that you haven't seen yet. So you need to do some domain averaging. What we're going to do is figure out some way to get those weights, and then do the simplest possible thing is just, according to those weights, average the representations that the experts predict. You can do this at the logit level. You can do it at different levels. It's all fine. You can think of this as a parameter-free mixture of experts. And it's pretty straightforward averaging going on here. So we're going to have this kind of prior over what domain we think we're in, given the text we've seen so far. And then these are the experts. So given what domain we think we're in, what does each expert think about what token's going to come next? And so the real hard part here is just figuring out, given what we've seen so far, what domain do we think we're going to be in? And then we're just going to weigh the experts' predictions according to that. It's a very straightforward approach. Figuring out where we think we are so far, again, not so complicated. We're going to have 2 terms here, a term of basically, you just use Bayes' rule. So we're going to have this term here. How much does the expert like the text that we've seen so far? What's our prior beliefs about which experts are more likely? And then a normalization constant just to turn it into a well-defined probability distribution. Right? So the likelihoods of the text we've seen so far according to different experts, some sort of prior, and some sort of normalization to make it a distribution. Right? Is it clear to everybody? Now, just one more slide on this, just going one more level into my recursion. How do we do this prior, or how do we update this as we go? I won't go into the full details. You can look at the paper. But there are many different reasonable approaches. And if you're a pre-deep learning person, you know about these Bayesian inference and priors. This is all kind of natural to you. So you could have a uniform prior. Every domain is equally likely. That's a reasonable starting point. You can actually do an updating prior, where as the text is streaming in, given the text you've seen before, you sort of update your beliefs about which are more likely, either at chunk level, document level, all sorts of different levels. That's fine. Or the sort of convenient thing, which is a little bit cheating, I want to be honest about this, a little bit cheating, is that you assume you have a small sample of data from your test domain, and you just compute the weights based on that. And you do it as a pre-processing step, and you just cache it. And we do that for convenience. It's just simple. So when I get a new domain, I don't need to know what domain it is, but I do need just a small sample of text from it. I can compute these weights, how much the experts like them, and then I'm just going to cache that and go forward. You can do all these things. They all work, but for convenience, this gives a nice results, and we just kind of stick with that. Okay. So now that's how we do the ensembling. How to do the averaging? It's very, very simple. So if these theta are the parameters of the elms in our elm forest, those are those different transformers. These weights are from the last slide, the exact same domain weights that you would do for ensembling. You literally just average the model's parameters according to how much they like the data. And it's important that this is not uniform here. If you did this, it wouldn't work. And it's important how you train it to set it up so that they're averageable. And I'll talk about that over the next few slides. But this is it. This is how you do model averaging. And it's sort of a model soup idea.
Here it seems you are making a new model for every document. I mean, it's not a new model, but is it?
That's correct. So, a typical MOE or conditional compute, you do the routing in the forward pass even at the token level often. This is, you could think of this as document level routing or domain level routing. And you just kind of do it once early and you cache it. That's one sense in which we're trying to design the simplest possible approach. We have no token level. I mean, you can readapt it every token if you want, but you don't need to. It works really well without it. And we're trying to simplify and streamline. Yeah, great question. You can absolutely keep them on separate GPUs and do routing.
I'm just trying to understand the same inference cost of the single expert. Isn't the cost the experts?
Yeah, so we'll come back and talk about that. One trick in general, I have a slide on this later, but for conditional compute in general, it's really hard because you need to decide how many experts are getting activated for each input. If you have sparsity, so you only need to use 1 or 2 experts, then you'd have whatever that 1 or 2 is times the cost of a dense model, because usually each of the experts are the same size as a single dense model. But here, because we're averaging, that's right. And that's more relevant for the last slide where we're doing ensembling, not for this slide. So the cool thing about this slide is that you have a single new model. So after you do the model averaging, you have a new custom dense model just for your task, and you just do everything inference as if it was a dense model.
Well, these are all the weights in
The entire network. So if you've seen model soups, you just average everything. It's really wild. It works. It's really beautiful. One more, and then I'm going to push forward. Yeah, so great. Why in the world does this work at all? Like, how can you average these things to get something sensible? You absolutely cannot do this with random models. Or actually, there's some great research I was talking about yesterday in the reception where you can sometimes. But we're going to train them very carefully from a common seed to make sure this works. And that's what I'm going into next. Yeah, so it won't be hyperparameter specific. It'll be data specific for us, but that's absolutely the right intuition. That's right. Okay, so let's move forward to learning and ask me more questions as we go. So how do you learn at Elm Forest? The naive thing would be to just train, if you want k different elementary models in your big bag of models, k different models independently of each other. Just divide up your data, train them. Does not work. The averaging won't work. Other things won't work. You won't optimally divide your data. You need to think a little bit more carefully about sort of getting a common core and how to set up a procedure so the models are all kind of related to each other. They're sort of variations of each other, specialized to different parts of the data, but with a common core that they've built on. And that's this branch train merge algorithm. I'll show you the whole algorithm here, but I don't expect you to get all the details yet. This is the overview. And then I'll take you through each step one slide at a time, and then we'll look at the slide again at the end, see how it all comes together. But the key thing to understand for now is it's going to be an iterative algorithm where you do rounds of training new models and throwing them into that bag and getting it bigger and bigger. But crucially, it has a step 0 initialization where you train a single seed model, a fair bit, to get a good starting point from which you're going to branch and train other models later. So I'm going to take you through this step by step from 0 to 1 and then through the iteration. 0 and 1 are basically all the work. 2 and 3 are very, very simple. And then we can sort of think about the implications as we go. So what kind of model are going to want to start this whole process up? So this seed training is critical. It's critical for the ensembling and the averaging to actually work. Because in some sense, you need to train a core that you're then going to specialize to different data. And then if they don't move too far from each other, the averaging will still be happy. Okay? We're going to want a good heterogeneous data mix. You want to be pretty careful with your seed to make sure things work. And in general, in the paper, there's lots of details about how much seed training should you do versus other, but I'm largely going to skip that for time today. But you can look for lots and lots of details. But now we have kind of this core model that sort of is pretty general. Could even be trained as much as a llama or something, but maybe a lot less. And then we're going to start branching from that. When you branch a model, what happens is, and you can do this in parallel for many different domains, but you basically get a new tranche of data for your new domain. It could have been in the original, it could be entirely new, but it's sort of domain-specific data. And the cool thing now is that we can use those inference ideas we had. So like, how do we initialize? We could just pick the nearest model from our set and initialize from that. We could always initialize from our seed. But actually, the thing that we found best empirically is to take the whole set of models you currently have, compute those weights that you would compute during inference, do your model averaging, and make a custom new model that looks as close as possible to your new data, and then start training from there. So it's a way of kind of pooling across the whole set of information you've learned, and then further specializing to the new data that comes in. And that seems to work, really quite well. Okay? And then that's basically it. You train in parallel. For each round of the algorithm, you can do that custom for, you can do as many different domains as you want in parallel. And then, in the future, you could think of much better ways of compression and stuff, but for now, we're just going to throw them into the bag after we're done. So the sort of set of models is just going to grow as you do more and more iterations of the algorithm. And that's the overall approach. Does that make sense? Okay. So I'm going to show you a bunch of different as many evaluations as I have time for, and give you a glimpse of kind of, crucial to this algorithm in particular is knowing the domains, right? So I have to know how to divide the data with metadata in advance, but that's what I'll give you at least a glimpse of how we relax at the end of the talk. There's a bigger issue here of kind of how do you compare dense and sparse models? And this is almost like a meta discussion. Since sparse models are becoming popular, it's worth just thinking about this independent of anything else I talked about today. That's right. So I'll show you results testing in domain and testing out of domain even. So not even more than you can train for, but what happens when some new domain happens. Yeah, that's right. And I'm not going to give you a perfect solution to kind of this slide here, dense versus sparse. But one thing I want to highlight is that we're really obsessed with parameter counts. Like we're really obsessed with is it a 10 billion model? Is it a 7 billion? Is it a 70 billion? Once you go to the land of sparse, like parameter counts are just bizarre. It doesn't make any sense anymore. You could talk about how many get activated on average for an input. You could talk about lots of different things. When you compare the mixed row models to the dense models, like those numbers are just now confusing. They're not comparable in any interesting way. And really what you should do is think about things like how much compute went into training, or what was the training speed, or what was the inference time. And I'll do various kind of normalizations when I do the evaluation, but just stop being obsessed with parameter counts. They don't make sense in the conditional compute regime because it's just, you don't know how they're actually being used or how many of them are actually being activated. I won't, I'll sort of blaze through the results in various ways. I could, do an hour on the results. There's so many experiments in these papers. They're highly empirical. But one thing you could do is say, okay, if I had, modest scale, sort of 8 training domains of these various different sizes, and then again, like the great question just now, I really, really care about testing on data I've never seen before. So, okay, if I get some gains on my training domains, you're not surprised. We all know that specializing language models for domains helps. And I literally saved that model that I specialized in my soup. But how do I do on new things I've never seen before that I didn't actually specialize for? And do I get gains there? That's the hard part. Okay. And then, so these are going to be all out-of-domain results. I think mostly I cut the in-domain results because the out-of-domains are the more interesting ones. These are different model sizes. This is a dense model. This is that baseline that we had done previously where we still had to do half of the synchronization. And this is our new version where we don't do any synchronization. If you're not used to interpreting perplexity, this is just a bunch of numbers, but lower is better. And a difference of 1 at these model scales is a lot. Okay, so we're getting nice gains here versus the previous baselines. And then if we compare the averaging versus the ensembling is better, which I think is not too surprising because you keep more parameters around overall. You're sort of activating more of the network. But the averaging is still getting a nice gain, and it has interesting compute accuracy trade-off. You also get increases in training speed, and this is because we do less network synchronization. So the models overall train faster. And then we looked at various scaling trends. So we said, okay, 8 versus 8 domains is not that different? What if we did 64 domains? And you can look at the paper. We did this, I think, 3 rounds where we sort of did 8, and then, it was 4, 8, 16 or something. You can sort of play with the ensembles and exactly how many rounds of the algorithm you do. And, we have by no means the optimal recipe, but we've just done some first explorations of that space. And you get, pretty nice results. So what I'm showing you here is actually another one of those normalizations. So this is where the x-axis is controlling for training cost in GPU hours. We're looking at the ensemble of one of our models at the end of all those rounds versus different points of dense training here. And the nice thing is we're getting sort of saving up to 2.5 times the training compute by getting a model that's really quite good. Okay. And then finally, if you want to have efficient inference, you would like these models to be sparse. So what I'm visualizing for you here is those mixing weights that we talked about. Both across the 64 different domains we trained on, and then 16 different domains that we're testing on here. And the nice thing is that, there's a lot of zero entries here. So you can get really good performance when you're doing your model averaging or whether you're doing your ensembling, just using 1, 2, 3 different models, something like that, the closest models. And this is an equivalent visualization that I'll go over a little bit faster, but this is the number of inference parameters, which is the same thing as kind of how many of the models you actually use. Of course, it does get better as you add more and more models, but even just using 2, 3, 4 gets you a lot of gains relative to using all 64 that we trained. Okay, so we're getting the nice scaling trends that we hope to see here. So to summarize part 1, stronger, modular, more efficient. I didn't go into it much here, but especially relative to the panel that just happened, there's a much stronger notion of data provenance here. You can actually track which parameters of your model were trained on which data in a very granular way that people don't usually do. And I'm very excited to kind of follow up on that in future work, although I didn't really have a lot to say today. But the key thing for today was about embarrassingly parallel training in this decentralized setup. And I have a whole nother section, but you can ask a quick question.
That's a good question. Is there any way to, like, the models could slowly diverge and maybe some models no longer make a good contribution to the average? Have you some way to pull them back or maybe cull them if they...
Yeah, so like pruning the set of models or updating them over time is, I think, really, really great future work. We just haven't got to it yet. One quick one. That's right. That's right. That's correct. Yes. Great clarification. Thanks. Okay. So let's talk just a little bit about how we get rid of that assumption of domain, that we know what domain it is. Show you a little bit more results, and then I'll take the question time, okay? And here I'll just give you the sort of caricature of it, because it's actually pretty straightforward, although a lot of hard empirical work to actually prove it. But the idea is basically, instead of using metadata to divide up the data, let's just do clustering. Let's do a very simple baseline. So if you're a type of NLP person like me, you spend a lot of time obsessing about data, looking at your data. And it turns out document embeddings, basically any way in the world you can embed a document, if you cluster over it, domains will pop out. Not always perfect domains, not always anything, but even TF-IDF or even BERT or any document embeddings you have, it's not hard to get domains to pop out. And so we did a very careful empirical study of that, and it allowed us to do lots of different scaling trends. Because when you have metadata for domains, you can only have so many domains. It's a lot of work to do it. But if you just use automated clustering, you can do a lot more scaling, you can do a lot more variations, and you can really try to understand the behavior of these models. So the actual setup that we did was, we just said, let's keep it simple. I have this mindset, like simple methods at as big a scale as we can afford. So TF-IDF document embeddings, it was fine. We also played a little bit with your favorite BERT and models. Doesn't matter. It's all fine. I'm sure in the future you can improve it. And then k-means clustering, intro ML, with one twist that you need to do balanced clustering. So there's a little bit of kind of bipartite matching going on to make sure that each of the clusters get an equal amount of data. There's a little bit of Hungarian algorithm hidden in there. You can look at the paper for details. But to a first approximation, this is just really, really simple with a little bit of extra work to keep it balanced. And then the cool thing, so that I changed, the algorithm's going to stay the change. The algorithm is going to stay the same. I'm only going to change step 0 and step 1. So this is how I change step 0. Step 1, cool thing now is I can seed from anything I want. And so at the time we ran these experiments, OPT was a convenient model for various reasons. You could rerun them all now with Llama 3 from yesterday, whatever you want. But now your seed models can be sort of open source, fully trained models that other people have shared. And you can start branching from that. And it's fine, and it works well, and it gets you better results. Okay, you train in parallel on those clustered domains. You merge it back in. Oh, and one other wrinkle I forgot is you change inference a tiny bit. So remember, I had all that work with the Bayesian priors and everything. Now that I have cluster means, I can just go through and just put a distance metrics on those cluster means for any particular thing and just get really nice mixing weights that way by looking at the current data point, how far it is from the various cluster means. So that works really well. Okay, and look at just a little bit of results. So how does the cluster compare to the non-cluster version? Here, we're not necessarily looking to get a gain. We just want them to be the same. And this is a pretty big scale on the pile, which is a relatively large open data set. And it is. The gains are smaller here overall because it's at bigger scale, but we're doing just as well. And then we can do a bunch of experiments to scale up. So this is not the most giant scale, but Sachin and Margaret spent some time at Meta even while they're at UW, and so we're able to scale up a bit. And we see some really beautiful trends. So this graph, to unpack it a little bit, each of these lines is a different data set size. So we're asking, as you grow the data set size, and again, this is perplexity, so lower is better. As you grow the data set size, how many clusters of data should you have? How many of these models should you have? And this was just one round. You could do a whole nother version of this with multi-round. And you see this beautiful trend where there sort of is an optimal number of clusters or subsets of your data, and that grows as the data grows. So as you get more and more capacity, as you have more and more signal, you can specialize for more and more different subparts of the data. We also did comparisons. The dream here, the sort of long-term goal would be that you could have a collection of small models, which together, when trained on this beautiful method, or two versions of it we're going to have to invent, or 5 versions that we're going to have to invent, but eventually we'll get to the point where you can put together a bunch of small models and you can beat a big model. Okay, we're not there yet, but we're getting some early signs that that may be possible. And so what you're seeing here is 16 clusters versus 1 cluster, where 1 cluster is a bigger model and 16 clusters is a bunch of smaller models, and different training budgets as we're training on more and more data. And we're getting this nice kind of trend, but we don't yet have like 1,000, 1 billion models could beat a 200 billion model or something like that. And that may never be possible. There may just be some things that only emerge at scale. The biggest risk for this research agenda is that small models together just won't be able to get there. But we don't know. Maybe it will. The talk yesterday gave some sign that small models might be fine if you do synthetic data. So maybe you integrate this with synthetic data. Maybe you do other things. Okay. So in conclusion here, we're just, this little tweak, we can get to arbitrary data sets. We can do much more careful studies of scaling. There is tons and tons of experiments in the paper. I encourage you to go look if you're interested. Moving forward, we want to go towards this decentralized future. We really want sort of all the pieces trained independently and contributed back together. But there's also lots of sort of technical challenges. So the clustering and the data modeling, being flat doesn't make sense. Could you go hierarchical? We've done some follow-up experiments. Everything in this talk was perplexity. You do get gains on downstream tasks, but the trends are different. And you can look at the papers for details, but there's more work to be done there. And then this kind of notion of sort of data provenance that I sort of hinted at a little bit earlier, we haven't developed it enough, but especially relative to the panel discussion we just had, I would argue that it's sort of insecure and maybe even fundamentally sort of unethical in a way to train a single model on all the data, which is the current regime. So imagine you're writing like a middle school writing tutor. Don't put the toxic data in there. Just don't do it. It's unethical. There's toxic data. Don't train on it. If you're building a hate speech filter for Meta, put the toxic data in there. It's absolutely crucial. You won't get performance without it. Is there a single model that can be trained on all the data that actually works for both use cases? Is there an ethical way to do that? Actually, not super clear to me. It's interesting to think about for the future. And regardless of what you should actually do, we should at least have mechanisms and algorithms and tools for thinking about these issues. So that's what I told you about today. And thank you, and I'm happy to take questions. We have time for a question.
Thank you. Thanks, Luke. Great talk. I had a question about part 2, where you talked about starting from the OPT series of model.
Yeah, that's a great question. It is the same paradigm as part 1. In the part 1, we kind of trained the seed model not as much as OPT, but anytime you do further training of a model, you got to play with your learning rate. You need to do various things, but it's all kind of standard. And at least 5 years ago or more, we discovered that further pre-training, like don't stop pre-training, this kind of thing always helps. So sort of the background premise is that when we were doing this work, is we know that if you specialize your data and further train a model on it, it will get better. Even the biggest models in the world are still this way. So let's think about how to leverage that to get some more interesting designs. That was kind of the premise.
Would you be sharing the slide deck?
I'd be happy to share the slide deck.
So this is it's super cool because you captured, I think, a lot of the benefits of these smaller models, boosted trees, adjacent method. One thing that stuck out to me is, I didn't see in your presentation, is when you take the domain-specific model and you average the weights, is that model, like what contribution does that model then make? And the reason I bring that up is for an overfitting problem, right? Because if you, for example, have like a music model, probably more specifically the cancer diagnosis model, right?
Sure.
You see some new sample you have never seen before. Does that cancer diagnosis model that's a lot smaller, it's constrained, does it then make a diagnosis that's off because it hasn't seen that data and you have a smaller overfit model? So that's my main question for you.
Yeah, you definitely need to worry about overfitting in general. That's a real issue. I think that we had some results kind of showing the mixture weights a little further back, which were very sparse. And so the real question is sort of, are you going to have a few domains from training that are similar to what you're doing at test? The domains that I can show you the slide. There was actually a fair bit of shift in the domains we chose. So there's some redundancy, but if you pick something that's just like wildly different than anything you've seen before, you're gonna be out of luck. If you pick something that's very close to what you've seen before, then you need to have trained those expert models carefully so they don't overfit, which people kind of know how to do with LLMs. We're probably not perfect, but we're pretty good at it. And then we'd sort of fall back on all those mechanisms to make sure that we don't overfit. So there's kind of those two cases you're worried about, and in both cases we have some sort of story, but I'm sure it's not perfect.
One last question.
This is pre-training, but then there's also like like instruction tuning and alignment. And how do you do that in in your more complicated setup? I mean, as opposed to just having a single model which you instruction fine tune or align.
Yeah, great question. I mean, I think that we haven't really explored that as much as we should, and it's really interesting to explore. When I look at, so there's kind of RL, PPO style alignment, which maybe we'd have to think about that, but it's not that different. But to a first approximation, when I think about alignment, I really just think of further pre-training. The sort of distinction between pre-training and alignment, I hope it's going to go away soon. And you see it already happening. People are being kind of secretive about it, but you see like more of the NTAS data kind of shifting over since Mistral and others. There've been a lot of tricks going on. So conceptually, mathematically, it's fine. Like you can run all these algorithms, you can train the models, you can divide up you can just either align all the elms independently, or you can divide up and align as appropriate. Of course, there's lots of details to work out. Conceptually, it should be possible. We just haven't got to it yet.